Welcome back to Math 40. Today we're going to continue with lecture notes week 9. We're actually going to finish up that set of lecture notes starting at page 14 on problem number 10. Now if you're in one of the sections that have already completed part of this problem, you can fast forward the video to the section where we last left off, but I am going to start this problem from scratch. Alright, so for problem number 10, they're asking us to graph one complete cycle of y equals negative 1 minus 3 secant pi x over 2 plus 3 pi over 4. And last time we saw that what we do is we consider the reference function, which is always going to be the reciprocal function of either the secant or the cosecant. So in this case, since we're working with secant, we're going to be looking at cosine. That means that our reference graph is going to be y equals negative 1 minus 3 times cosine of pi x over 2 plus 3 pi over 4. Okay. Now, if we pretend that we were graphing only this problem, the first step that we would take would be the primer step, step 0, in which we consider only the trigonometric term of the equation. So that means that we're going to be considering y equals negative 3 cosine of pi x over 2 plus 3 pi over 4. And then we do want to pull out the coefficient of x so that we're able to replace the x minus or plus a constant by theta. So if we do that here, we're going to end up with negative 3 times cosine of, the coefficient of x is this pi over 2, so we're going to pull it out, pi over 2 times x plus, in order to find out what's left in the second term, notice that factoring is always dividing by the factors. So here we divided by a pi over 2. Here if we divide by a pi over 2, we can do some side work to figure out what's going to get left over. So if we take 3 pi over 4 times reciprocal of pi over 2, that's the same thing as dividing. So that would be 2 over pi. The pi's are going to cancel. We're going to get a 6 over 4, but a 6 over 4 will reduce down to a 3 over 2. So we are going to get here plus 3 over 2. Okay, and so now that we have that, we're ready to replace by theta. We're going to let theta be the x plus 3 pi, plus 3 over 2, and that gives us an equation that looks like y equals negative 3 times cosine of pi over 2 theta. We're now ready to consider the rest of the steps. So step 1 is usually the step where we find the period. So the period is going to be a 2 pi over b. In this case, our b is a pi over 2. So we'll have a 2 pi over 2, which becomes a 2 pi over 1 times a 2 over pi. Now the pi's are going to cancel, and then 2 times 2 is going to give us a 4. Right, the next step is to find the step size. And the step size is always the period divided by 4. So in this case, we're going to have a 4 over 4, which becomes 1. Then we find the important x values. In this case, we do have a shift, so that means that we're actually first considering the theta values. So starting with theta 0 being 0. And then the next theta value is going to be 1 times the step size of 1, which is just 1. Then 2 times the step size of 1, which is 2. Then we're going to have 3. And finally, we're going to have 4. Okay, so that is without the shift. We want to consider the original variable, which is x. So we're going to go back up here where we first wrote the relationship between theta and x and solve for x. That means subtract the 3 over 2 from both sides of the equation, and we're going to end up with x equals theta minus 3 over 2. And so that means that with shift, we're going to have first x0 being theta 0 minus 3 over 2. Again, this is just applying the formula. And then replacing theta 0 with 0 means we have 0 minus 3 over 2. So we're going to get a negative 3/2. Repeat the process for x1. It'll be theta 1 minus 3/2. And that is a 1 minus 3/2. A 1 is the same as a 2 over 2. So 2 minus a 3 will give us a negative 1/2. Next one, x2 will be theta 2 minus 3 over 2. Theta 2 is a 2, so we're going to have a 2 minus 3/2. A 2 is the same thing as a 4 over 2, and a 4 minus a 3 gives us a 1/2. Okay, next one, repeat the process. Okay, we're going to have a 3 minus 3/2, and that's going to end up being 3/2. And then the final x value, which I'll squeeze over here to the right, will be a 4 minus 3/2. This is the same as an 8 over 2, so 8 minus 3 will give us a 5/2. The next step is to transfer over the x values to our table of points. So the first relevant x value is negative 3/2, followed by negative 1/2, 1/2, 3/2, and 5/2. Now remember, we're first going to be graphing cosine, the reciprocal graph. So I'm going to take a separate row down here below the table of points to find the relevant or the corresponding y values of negative 1 minus 3 cosine of this argument. Okay, so I'll go ahead and write that down here. Okay, and then it's probably a good idea to punch these into our calculator just to make it a little bit faster for us. So we'll have a negative 1 minus 3 times cosine of pi times, I'll just write this as a pi over 2 times x. So we'll have a pi over 2 times x. In this case, x is this negative 3/2 plus a 3 pi over 4. And the first y value that we get is a negative 4. Remember, this is not for the final answer, it's for our reference graph. And then we repeat the process, but we do want to have a negative 1/2 instead of a negative 3/2. So I'm going to go ahead and replace that 3 with a 1, and we get a negative 1. Okay, the next x value is a 1/2. So I'm just going to take away this negative. We get a 2. Next one is 3/2, so change this 1 to a 3. We get negative 1. And last one is 5/2. So I'm just going to change this 1 to a 5. And we get negative 4. Okay, so let's draw the reference graph. We need to make sure that we have negative 3/2 on the left hand side and up to 5/2 on the right hand side of the y-axis. So starting with the negatives, I can make this a negative 1 and this a negative 2. That would place negative 3/2 here, and this would be negative 1/2. On the right side of the y-axis, we can make this a 1, this a 2, this a 3. And that means that halfway we would have 1/2, and then 3/2, and 5/2. Okay, now corresponding y values, at negative 3/2 we have a negative 4, and that is the lowest y value that we get. So I'll go ahead and make this 2, and this a 4. That'll place 1 point, actually I went one tick mark too far to the left, so negative 3/2 comma negative 4, then negative 1/2 comma negative 1, that'll be here. And then 1/2 comma 2. So this is a 2. I'll place it here. 3/2 comma -1. So that would be here. And 5/2 comma -4. So down here. That means that we have a cosine graph, and I'm drawing this in a dashed line because it's not the ultimate graph that we are considering. We are considering secant, but that is what the cosine graph look like. Okay, now let's think about what's happened to this cosine graph. The cosine graph is not oscillating about the x-axis, right? It has shifted down to oscillating about the line y equals -1. Right? That is the new axis of oscillation. And that means that what still makes cosine 0 in the case of this equation is going to be this x equals -1/2 and x equals 3/2. But because we have this -1 that is added to the trigonometric term, that 0 gets shifted down. But in any case, we are still going to have asymptotes along those usual zeros of the cosine graph. So we'll have an asymptote here and an asymptote here. We'll say these x values make cosine 0. Okay, then what? Then the trick that we learned to get a more or less picture of where secant would be is to simply flip the shape of the cosine graph, right? So if the cosine graph is facing up, it kind of looks like a parabola going up. We're going to have a parabola that faces downwards. In this case, it seems like we have a parabola facing down, so that means that secant will have a parabola facing up. And similarly, at this point, we're going to have a parabola facing down. And so once you've drawn the secant graph, you can, if you want to, erase these lines. To obtain solely the secant graph. Because the other ones, they're just being used as reference. So we're now going to begin lecture notes week 11. And if you take a look at the introduction, if you remember from the trigonometric equations that we were graphing, we used the fact that if sine was if sine was odd, then having a negative inside of the argument meant that we could bring the negative outside and multiply it with the function. Whereas if you had an even function like cosine, then f of -x is the same as f of x. So these equations are actually called identities. They are examples of identities because that is something that is true regardless of what value you replace for x. So it's true for every x, and when that is the case, you have an identity. And so those are just two of several other identities that exist for trigonometry. If you take a look at Canvas under the module for this week, you'll find a sheet that is called Formulas and Identities. And this contains several other equations that are true for any variable that you decide to plug in. So again, when you have that situation, then you have an identity. So we're going to be considering these to solve all of the problems in the lecture notes for the next couple of weeks. Okay. So let's start by looking at this first type of problem, which is finding the exact trig values of angles that are not on the unit circle. So on the unit circle, we found angles that are multiples of 45 or multiples of 30. And it allowed us to quickly pick out what is the sine, what is the cosine, and what is the tangent. For other angles that are not on the unit circle, such as maybe 15 degrees, we can still solve that without using a calculator by applying maybe sum or difference, double angle, or half angle formulas. So I'm going to start by looking at the sum and difference formulas. So sum and difference are found on the left-hand column at the top, on the right-hand column at the top. And we're just going to kind of dissect these a little bit. It looks a little bit scary because it has this plus or minus, but it's actually not as bad as it looks. This just contains two formulas in one. And on a sticky, for instance, I'm going to focus on this first one. I'm going to separate it into the two equations that are being contained here. So we have sine of A plus B, and I'm going to be using capital A and capital B instead of alpha and beta, so it doesn't look as scary. If we just focus on the top symbol, which is a plus, okay, so if we focus on the top symbol on the left-hand side, then we also have to pick out the top symbol on the right-hand side. And so that is saying that the sine of A plus B is the same thing as taking sine of A, taking cosine of B, multiplying it together, and then adding it to the product of cosine of A times sine of B. And that's the first equation that's contained in there. The second equation is if you take the bottom symbol, so on the left-hand side we have a negative, on the right-hand side we also have a negative. So the second equation, or the second identity, would be sine of A minus B is equal to sine of A cosine of B minus cosine of A sine of B. It's just the symbols change. For cosine, it's a similar idea. If I take just the top symbol, we would have cosine of A plus B is equal to cosine of A, cosine of B, minus sine of A, sine of B. And the reason being, again, is because if I take the top symbol on the left-hand side, then I also have to take the top symbol on the right-hand side. Okay, so if on top we have plus, then over here at the top we have minus, and this is the equation that we get. If we now consider the bottom symbol, then that means that we'll have an equation that reads, or an identity that reads cosine of A minus B is equal to cosine of A, cosine of B, plus sine of A, sine of B. Alright, so let's use the sum and difference formulas to help us solve part A, which is asking us to find cosine of 15 degrees. Now to solve this type of problem, what we do is we take the angle and we try to write it as either a sum or a difference of two angles that are on the unit circle. And so if we think about 15 degrees, we could take 45 degrees minus 30, and that'll give us 15. So I'm going to rewrite this as cosine of 15 degrees is equal to cosine of 45 degrees minus 30 degrees. Now the reason why we would want to do that is because now I can use one of my sum and difference formulas, specifically this last one that we dissected, because it falls in line with the form, right? We have the difference of two angles. The A in our case is 45 and the B is 30 degrees. And so therefore, according to this identity, what this should be equal to is cosine of the first angle, angle A, which is 45 degrees, times cosine of the second angle, which is 30 degrees, plus sine of the first, which is 45 degrees, times sine of the second, which is 30. And then hence the reason why we want to write it in terms of angles that are on the unit circle, because now we can simply refer to it and find out what is cosine 45, what is cosine 30, and same for the sine function. Okay. Alright, so here is my unit circle. I have it handy from a set of lecture notes that we've considered in the past, lecture notes week 3. And if I take a look at 30 degrees, cosine of 30 is radical 3 over 2. So this is going to be radical 3 over 2. If I take a look at cosine 45, that's going to be a radical 2 over 2. And then we have plus sine of 45 is also radical 2 over 2. And sine of 30 is going to be 1/2. Okay, so if we take this product here, we're going to end up with the square root of 2 times square root of 3, which is a square root of 6, over 2 times 2, which is 4, plus a square root of 2 over 4, because square root of 2 times 1 will give us still square root of 4. So altogether, the most we can do is combine the numerators into one fraction as square root of 6 plus square root of 2 all over 4. Okay. If we repeat the idea of with sine of 75 degrees, we're trying to write it as the sum of two angles that are on the unit circle. So we could potentially write this, or one way to do it, as sine of 45 degrees plus 30 degrees, right? Sine of 45 plus 30 gives us 75. So now if we look at the formula for sine, specifically the one that has plus, right, because that's the one that aligns with the form we have here, we get that A is going to be like the 45 degrees, and B is going to be like the 30 degrees. Okay. So now if we apply the formula, we're going to get sine of 45 degrees times cosine of 30 degrees, because it's sine of the first angle times cosine of the second. And then we have plus cosine of the first angle, so that'll be 45, times sine of the second, so times sine of 30 degrees. And so again, if we look at the unit circle, we'll find that the sine of 45 is radical 2 over 2. Cosine of 30 will be radical 3 over 2. Cosine of 45 is going to be radical 2 over 2. And sine of 30 will be 1/2. So in the end, we're going to have a square root of 2 times the square root of 3, which is a square root of 6, over a 2 times a 2, that's a 4. And then this is a square root of 2 times 1 over a 2 times 2, which is 4. So we end up getting the same answer, which maybe might seem a little suspicious to us. We can always double check on the calculator. So let's go ahead and do that. So if we look at the calculator, I'll make sure that I change to degree mode. Sine of 75 degrees is equal to 0.9659. And if I take a look at what is cosine of 15 degrees, we get exactly the same thing. So it must mean that these two fractions have to equal to this decimal answer. And we can double check. So let's take the square root of 6 plus the square root of 2 divided by 4. Make sure that you group the numerator together, otherwise you're just going to divide the radical 2 by 4. So grouping the numerator together gives us this decimal, which agrees with the cosine and sine. Okay, so that looks good. So for part C, we have cosine of 5 pi over 12, which means that we're switching now to radians, and there are two methods that you can take in order to approach this problem. The first one is you can change the radians to degrees by multiplying 180 over pi into this 5 pi over 12. And then from there, trying to find two angles that add up to the degree answer, or that subtract to the degree answer. The other option is to find what two angles in radians add up to 5 pi over 12, or have a difference of 5 pi over 12. I like to do it at sum to 5 pi over 12, because what I do, and this is more of a trial and error approach, what I do is I break up the 5 pi over 12 into the sum of maybe pi over 12 plus 4 pi over 12, right? And then I check if these two reduce to any answer, any angle that is on the unit circle. So if pi over 12 doesn't reduce, 4 pi over 12 reduces to a pi over 3. This is on the unit circle, but pi over 12 is not. So because there's at least one angle that is not on the unit circle, we kind of discard this possibility. The next possibility we can take a look at is now having the sum of 2 pi over 12 plus 3 pi over 12. Now if we write it this way, the 2 pi over 12 reduces down to a pi over 6, and the 3 pi over 12 reduces down to a pi over 4. Now both of these are on the unit circle, so because both angles are, we use that possibility. So coming back here, it means I'm going to write that cosine of 5 pi over 12 is the same as taking cosine of pi over 6 plus pi over 4. And now we'll go back to our formulas and identities. The formula that best fits the form we have here is this cosine of a plus b, where a is the pi over 6 and b is the pi over 4. Okay. So with that in mind, the identity reads that should be equal to cosine of the first angle, so that'll be cosine of pi over 6, times cosine of the second angle, so that'll be a pi over 4, minus sine of the first angle, so minus sine of pi over 6, times sine of the second angle, so that'll be times sine of pi over 4. Okay, again, let's go to the unit circle. Here is pi over 6. Cosine of pi over 6 will be a radical 3 over 2. Pi over 4 is here. Cosine of pi over 4 is a radical 2 over 2. Okay. Pi over 6 is here again, and sine of pi over 6 is 1/2. And finally, sine of pi over 4 is here, and sine of pi over 4 is radical 2 over 2. Okay, so what do we get? Radical 3 times radical 2 is a radical 6 over 2 times 2, that's 4, minus 1 times radical 2 is radical 2, over 2 times 2 is 4. So the final answer is square root of 6 minus square root of 2 all over a 4. Okay, we're going to attempt one more problem of that type. In this case, we have a 7 pi over 12. So we'll go through with that same trial and error approach. So we'll first start maybe with pi over 12 plus 6 pi over 12, because together they add up to 7 pi over 12. But the issue with that is that the first fraction, the pi over 12, is not going to reduce down to anything useful, nothing on the unit circle. Alright, so this one doesn't work because the first fraction is not, the first fraction fails. The next one to try is maybe a 2 pi over 12 plus a 5 pi over 12. Now in this case, the 2 pi over 12 reduces down to a pi over 6, which is on the unit circle, but the 5 pi over 12 does not reduce, and that is not on the unit circle. So that means we don't use this option. And the next one we can try is a 3 pi over 12 plus a 4 pi over 12. And 3 pi over 12 will reduce down to a pi over 4. That is on the unit circle. And then the 4 pi reduces down to a 3 pi over, a pi over 4. Alright, divide top and bottom by 4 and we'll get a pi over 3. So this is also on the unit circle. That means that we can write down 7 pi over 12 as a sum of pi over 4 plus pi over 3. And so we'll write it here. Tangent of 7 pi over 12 is the same as tangent of pi over 4 plus pi over 3. And now we didn't really dissect the formulas for tangent, so let's look at them directly on the formula sheet. Okay, the one that we're looking for is one that has plus. So here, that would be the top symbol. And so picking the top symbol on the left-hand side means picking the top symbol everywhere on the right-hand side. Okay, so let's write it here on our sticky note. We'll have tangent of a plus b is equal to, in the numerator, tangent of a plus tangent of b. So that's tangent of a plus tangent of b over 1 minus tangent of a tangent of b. Okay, and so now that we have the formula, we can come to this problem and start replacing in some values. So tangent of a, that's pi over 4 plus b, which is pi over 3, will be tangent of the first angle. That's tangent of pi over 4 plus tangent of the second angle, that's tangent of pi over 3, divided by 1 minus tangent of the first angle times tangent of the second angle. And all of that is in the denominator. So we can refer to our unit circle, and in the unit circle, what we have to keep in mind is that we have explicitly sine and cosine. Cosine is the x-coordinate, sine is the y-coordinate, but we can always find what tangent is by remembering that tangent is y over x, or in other words, sine over cosine. You can also find that same formula that I just mentioned on the formulas and identity sheet at the very top. Okay, tangent of angle theta is going to be sine of angle theta divided by cosine of angle theta. Okay, so here, what we're going to do is take the, look at pi over 4. So here's pi over 4. Take sine of pi over 4, which is going to be radical 2 over 2, and divided by cosine of pi over 4, which is also radical 2 over 2. So this is going to be just 1. We'll have a 1 plus. Now tangent pi over 3, here's pi over 3. We'll have y over x again, or sine over cosine. So that'll be a square root of 3 over 2 divided by a 1/2. That's the same thing as having a square root of 3 over 2 times a 2 over 1. So we're just going to get a radical 3. Okay, and then in the bottom we'll have 1 minus tangent of pi over 4, which we said was 1, times tangent of pi over 3, which we said is radical 3. Okay, so in the end, well, not completely the end, because we have 1 plus square root of 3 over 1 minus radical 3. And if you recall, we don't like to leave radicals in the denominator for any problem. So to rationalize 1 plus radical 3 over 1 minus radical 3, we go through the following steps. We actually multiply by the conjugate of the denominator. And the conjugate simply means we have the same two terms but the opposite sign in between them. So we're going to be multiplied by 1 plus radical 3 at top and bottom. And then if we distribute, 1 times 1 will give us this 1. Then 1 times radical 3 will be a radical 3. Radical 3 times 1 will also give us radical 3, so that's a total of 2 radical 3's. And then radical 3 times radical 3 will give us just 3. In the denominator, 1 times 1 will give us 1. 1 times a radical 3 will give us a positive radical 3. Then negative radical 3 times 1 will give us the negative radical 3. Negative radical 3 times radical 3 will give us a negative radical 3 squared, which is just 3, so minus 3. If we combine the like terms in the denominator, well, the plus radical 3 and negative radical 3 are going to cancel out, leaving us a 1 minus radical 3, so that's this here. And then in the numerator, if we take the 1 plus 3, it'll give us a 4 plus 2 radical 3. In the denominator, the 1 minus 3 will give us a negative 2. If we then take those two terms and split them up, we'll get a 4 over negative 2 plus 2 radical 3 over negative 2. And then the 4 over negative 2 will reduce down to a negative 2, and the 2 over negative 2 will simply reduce down to a negative 1, radical 3. So negative 2 minus radical 3 would be our final answer for part D. We're now going to take a look at a different type of problem in which we have more than one term and we have a product of potentially two trigonometric trigonometric terms, or maybe even squares, as in the case of G and H. So for this one, we have cosine of 87 degrees times cosine of 93 minus sine 87 sine of 93. So if we look again at the sum and difference formulas that we were considering earlier, it looks like this form might match one of the right-hand side part of an identity. In particular, if you take a look at the cosine of a plus b, that's cosine of the first angle times cosine of the second minus sine of the first times sine of the second. And that's precisely what we have. Where we have the product of two cosines of different angles minus the product of two sines of different angles. So this is actually going to be equal to cosine of the first angle, which is 87 degrees, plus the second angle, which is 93. And so 87 degrees plus 93 degrees is going to give us 180. And that means that we have a final answer of -1. And if this seems a little bit suspicious that we might have something as complicated looking as cosine 87 times cosine 93, minus all this other stuff be just 1, we can always verify on the calculator. On the calculator, let me just make sure we're in degree. Yep. If you take cosine of 87 degrees times cosine of 93 degrees minus sine of 87 degrees times sine of 93, we get -1, which is precisely the answer that we got from the law of cosines, the sum of cosines. Okay, similarly for part F, we have sine times cosine of two different angles minus cosine times sine of the same two angles. So if we consider which one best matches that form, we have sine of A times cosine B minus cosine A sine B, which fits perfectly with this. And that is equal to sine of the difference of the angle, sine of A minus B. So this is actually going to be sine of angle A, which is 40 degrees, minus angle B, which is 160. And so that's going to give us sine of negative 120. Now if you recall, sine is an odd function, which means that when we have a negative inside of the argument, we can bring it out. So we get negative sine of 120. And now if we use the unit circle to help us find what is sine of 120, we're going to get a radical 3 over 2. So this is going to be radical 3 over 2, but we can't forget to bring over that negative. So we're going to have a negative. Okay. The next problem reads sine of 15 degrees times cosine of 15 degrees. Now that doesn't look like any of these equations because all of these equations have two terms, right? They have the product of two trig plus or minus the product of two other trig functions. So it's not really any of these formulas, which means that we have to refer back to our cheat sheet and see if there's anything that might fit better. Yeah. So take a moment to look through the formulas. And there is actually one here that looks very similar to what we have. We have sine times cosine, and if you look at the fourth product to sum formula, and not the fourth, the third product to sum formula, we have sine of an angle times cosine of an angle equals 1/2 times sine of the sum of the two plus sine of the difference of the two angles. And so I'm actually going to write that formula over here so that we can compare it. And we have sine of A times cosine of B is equal to 1/2 sine of A plus B plus sine of A minus B. Okay, so now if we compare the two, this left-hand side agrees. So if we replace A with 15 and B with 15, that means that we have sine of 15 degrees times cosine of 15 degrees is equal to 1/2 sine of the first angle, which is 15. And I'll just go ahead and color code these. So we'll have 1/2 sine of first angle 15, second angle is also 15, plus sine of first angle 15, second angle is also 15, and that's a minus. So we get 1/2 sine of 30 degrees plus sine of 0 degrees. Sine of 0 will be 0. Sine of 30 degrees, if you refer to the unit circle, is 1/2. So we'll end up having 1/2 times 1/2 plus 0. And that's simply going to be a 1/2 times a 1/2, which is 1/4. Okay, next problem. This one is even more interesting because now we do have a difference of two terms, but there's a square involved. So product to sum is not going to be enough because product to sum is just product of two factors. And sum and difference is not going to be enough because we don't have a square anywhere. So the formulas that have a square are the half angle formulas, We also see Pythagorean identities having some squares in them. And we also have squares in the double angle formulas. The form that we have is cosine squared, cosine of one angle 15 minus sine squared of the same angle 15. And the one that best fits that form is this double angle formula for cosine. Okay. So cosine of 2 theta has 3 different applicable formulas. This is the first one, here's the second, and here's the third. But the one that we're going to focus on is the cosine squared minus sine squared. So let me write this down, the formula. We have cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And I'll just write here, this is a double angle formula. I didn't write it for this one, but I'll write it now. This was a product to sum. Okay. Now, because these two match, I'm simply going to write this as cosine squared of 15 degrees minus sine squared of 15 degrees. That is going to equal to cosine of 2 times 15 degrees. Right, I'm replacing everywhere there's a theta with 15 because these agree. Okay, then that'll give me a cosine of 30 degrees. And cosine of 30 degrees, if you take a look at the unit circle, that is going to be a square root of 3 over 2. Our final answer for this problem is a square root of 3 over 2.